So here we're going to talk about gas mixtures. This includes Dalton's law of partial pressures, how to deal with mole fractions if you have a mixture of gases, and then using these partial pressures to solve various problems with regards to number of moles of gas and things like that. All right, so Dalton's law of partial pressure. This states that the total pressure exerted by a gas mixture is the sum of the partial pressures exerted by each component of the mixture. So this is a little confusing. So here we have pressure total. That capital sigma, it just means the sum of the individual pressures. So this would be pressures of anything, like let's say you have a mixture of N2 and O2. You just add the partial pressure of O2 and the partial pressure of N2 together. And what this means is that when we have these pressure PV equals nRT, a lot of times it's been pressure total and then number of moles total. But we can do it for an individual pressure. So pressure associated with, let's say, O2, oxygen gas, would be equal to the number of moles of oxygen gas specifically. The temperature would be the same for the entire mixture, and the volume was the same for the entire mixture, since the volume, a gas encompasses the volume of a container. So it's a little strange, but you can kind of think about it like each individual gas is only contributing to some portion of the total pressure. If the pressure is a force over an area, these gas molecules very literally are running into surfaces, causing a pressure. They're applying a force over an area, let's say your skin, right? So the pressure that you're feeling is some associated with various gases. Most of the time it's nitrogen gas that is hitting a surface in a situation like air. A smaller portion of the time it's oxygen gas, and an even smaller portion of the time it's other minor components like CO2 or argon. So this is what we mean by Dalton's law of partial pressures. A lot of times I think it's easier to figure out what's going on here with some examples. But all right, so this is an example like that, where we have a 1 liter vessel. It contains a mixture of gases, both nitrogen gas and hydrogen gas at 25.5 degrees Celsius. There are 0.215 moles of nitrogen gas and a much smaller proportion of hydrogen gas, 0.0118 moles. We're being asked to determine the partial pressure of each component and the total pressure of the vessel. So this is how we would go about doing this. So we have the pressure associated with nitrogen gas. This is called the partial pressure of nitrogen. We're just using the moles of nitrogen. The temperature and volume is true for all of the gases, right? They're both occupying the 1 liter vessel, and they're at 25.5 degrees Celsius. So just plugging that in, again, remember your temperature needs to be in Kelvin. What it's saying is that the partial pressure of nitrogen is equivalent to 5.27 atmospheres. And then we can do the same thing with hydrogen gas, making sure to plug in hydrogen gas here. And we see that the partial pressure of hydrogen is 0.289 atmospheres. The total pressure is the sum of the partial pressures, right? So the partial pressure from nitrogen, the partial pressure from hydrogen will equal 5.56 atmospheres. That's the total pressure. So you can see most of the pressure is coming from nitrogen, which makes sense because that's most of the moles of gas. Okay, so this is what we mean by Dalton's law of partial pressures. You should also note in this, this will be more important later as well, the total number of moles of gas are also equal to the moles of N2 plus the moles of H2, right? And this is just a mixture of 2 gases. You could have 3 gases, 4 gases, so on and so forth. Same with the partial pressures. We commonly have 2, maybe 3 gases, but this is as many gases as are in the mixture. Okay. And this will kind of lead into the next idea along these partial pressures in Dalton's law. So again, we have Dalton's law of partial pressure. This is what we just saw. The pressure total was equal to the sum of the individual pressures. So that was pressure of nitrogen, pressure of hydrogen. And we had to make sure that if we're talking about a partial pressure of an individual component, we can't use the total number of moles of gas. We had to use the moles of gas associated with that particular gas. Okay. This leads into another idea called the mole fraction. So the mole fraction, it's this capital X sort of thing. It's a chi. So this is just the molar fraction. So it's the number of moles of that individual gas divided by the moles of the gas total. It's always going to be less than 1. So therefore the sum of the mole fractions for all components of the mixture is always 1. And these molar fractions are dimensionless because moles divided by moles. It's really important that this mole fraction, it's actually the same as if we do the same thing with the pressure. So the partial pressure of a particular gas divided by the total pressure is also equivalent to this mole fraction, this chi. So number of moles and pressure are proportional to each other. So if you have this molar ratio, you can multiply that by the total number of moles of gas, and that'll get you the moles of your individual component. Same thing with pressure, however, right? So if you have a certain molar ratio of a gas, you multiply that by the total pressure, and you'll get the partial pressure of that particular component. So this is really important. Essentially, what this is telling us is that the proportion of the moles is directly proportional to the partial pressure of the moles. So the partial pressure of that gas. So if 5% of the gas in a mixture is a particular gas, it's going to contribute also to 5% of the total pressure, right? That's what that mole fraction is. So let's go back to that question we just saw, okay? And we're going to add a little component to it at the very end. So take a look at this bottom component. So we can actually figure out these molar fractions, these molar ratios of nitrogen and hydrogen. So like I said, this is that capital X thing, the chi. So that's the number of moles of N2 over N total, which is equivalent to the partial pressure of N2 over the pressure total. And that is equal to 0.948, right? You add these two together, you equal 1. So this is 95% of the moles are associated with nitrogen and 5% of the moles are associated with hydrogen. So again, that also means that 5% of the pressure is associated with hydrogen and 95% of the total pressure is associated with nitrogen. Okay, so there's some similarities between this pressure and number of moles of gas. So conceptually, we really do want to understand this aspect. It makes some of these equations more intuitive instead of trying to memorize all these equations, because you're using them slightly differently every single time. But yeah, so it's this is a really helpful idea in terms of calculating either partial pressures or moles of a particular component and some things like that. All right, let's try another one of these. So in 1999, the FDA approved the use of nitric oxide to treat and prevent lung disease, which occurs commonly in premature infants. The nitric oxide used in this therapy is supplied by hospitals in the form of a nitrogen gas to nitric oxide mixture. So let's calculate the mole fraction of nitric oxide in a 10-liter gas cylinder at room temperature that contains 6.022 moles of N2, and in which the total pressure is 14.75 atmospheres. So it's a compressed cylinder because we have a higher pressure, right? 14.75 atmospheres. And that is the pressure total. It is important that we note that that's the pressure total. That is not the pressure associated with nitric oxide, however, right? Okay, so let's start plugging in some of these. Here we have P total, 14.75 atmospheres. The moles of N2 are 6.022 moles of N2. The temperature is 298.15 Kelvin. Okay, so we can get to the moles total in the cylinder because we have the pressure total, right? So this 6.029 moles of gas, this is all of the gas. So this is both N2 and NO, right? So if we wanted to get to the moles of NO, that's just N total minus the moles of N2. So 6.022 moles of gas total minus 6.022 moles of N2. We only have 0.007 moles of nitric oxide. Okay. So we could get that mole fraction, so moles of nitric oxide over moles total. That gets you 0.001. that's 0.1% of the mixture is nitric oxide. So it's interesting that they have a tank of nitric oxide, but it's nearly all nitrogen gas, right? I mean, it's a very low concentration of nitric oxide. It's only 0.1% of the moles of gas. So you could actually do further calculations with this and take a look at the partial pressure. So the partial pressure of nitric oxide in the 14.75 atmospheres is only 0.01475 atmospheres, right? It's a very small portion of the partial pressure is coming from nitric oxide. The rest of it, nearly all of it, is coming from nitrogen gas. All right, so another aspect of gas mixtures, which a very common lab that is run is based on this. So here we have something like zinc solid or some metal that reacts with an acid, and it'll produce hydrogen gas. So here you can have a reaction mixture, let's say acid plus a little metal strip. So here's like the little metal strip that you have in there. You drop it in, and then the gas will escape into a closed container where you can measure the volume of that gas. And so you're collecting that gas over water. So there's water in here as well. So this actually ends up being a gas mixture. It's not just hydrogen gas that is being produced. You also have some water vapor that's in that location. Okay, you're assuming the zinc is totally used up, or whatever metal you have. You'll know that because it completely dissolves. You'll see the zinc go completely away. So all of that was converted into hydrogen gas. So you can do math here with stoichiometry to figure out the number of moles of gas that have been produced and some things like that. But you have a mixture of gases here. So we're going to deal with, we're going to figure out how to deal with that. Okay. Luckily, the vapor pressure of water, so the partial pressure of water, is a function of temperature. So as you may be familiar with, the higher the temperature, the more vapor pressure you would get for water, the more essentially increasing the humidity in that interstitial space, right? So the pressure in torr, remember 760 torr is 1 atmosphere, which was the same as 760 millimeters of mercury. So let's say at a normal room temperature condition, like 25 degrees Celsius, we're seeing that 23.8 torr is associated with the partial pressure of water. So that's a small portion of the total pressure, but it is a non-insignificant portion. So the pressure in the total pressure in that container is going to be the sum of the pressure of water, the partial pressure of water, which we can get from this table, plus the partial pressure of hydrogen gas, which is probably what we're more interested in. We're more interested in the chemical reaction that we ran and the partial pressure of that hydrogen. Okay, so this is what one of these might look like. So let's say you have calcium metal, you're going to react it with water, and you're going to produce hydrogen gas. Calcium is very reactive as a metal, so you actually don't even need an acid. You can just use water, and it'll do this. So we're producing hydrogen gas as water, as a product, and we are collecting it over water. So it's very important that we see that the gas is collected over water, because that means that we know it's not going to be pure hydrogen gas that we're collecting. We're going to have a mixture of gases in that final product, in that final container. So it's going to be hydrogen gas plus water as a gas, water vapor. Okay, so let's determine the mass of hydrogen produced at 25 degrees Celsius and 0.967 atmospheres when you have 525 milliliters of the gas collected over water. Again, it's the gas mixture that we're referring to. So again, we have the partial pressure of hydrogen is the pressure total minus the partial pressure of water. So here 0.967 atmospheres is the pressure total. We're going to subtract out the partial pressure of water. Again, we can get that from the chart. So it was, you look at the partial pressure of water on that chart at 25 degrees Celsius, which is what we're operating under. That was 23.8 torr, which we could convert to atmospheres. So that was 0.0313 atmospheres, recalling that 760 torr equals 1 atmosphere. So we can get our partial pressure of hydrogen. Our partial pressure of hydrogen is 0.936 atmospheres. We cannot use the pressure total when we're going to be using PV equals nRT. We're interested in the moles of hydrogen gas, not the moles of gas total. So if we want the moles of hydrogen gas, we need the partial pressure of hydrogen gas in our PV equals nRT. So we have to plug in 0.936 atmospheres, not our pressure total. Remember that pressure was associated with water and hydrogen. We want just hydrogen here. So we can do this. Volume, convert to liters. Temperature, convert to Kelvin. Our R is good to go. And we get 2 times 10 to the negative 2 moles of hydrogen. And then we can easily convert that to grams of hydrogen. So we get 0.0405 grams of hydrogen. Okay, we would have been slightly off if we used the pressure total as opposed to the partial pressure of hydrogen. So this is essentially kind of the applications of Dalton's law of partial pressures. Let's try another one of these. We have a large hyperbaric chamber. They're used to treat victims of diving accidents typically. In one treatment protocol at a typical facility, the chamber is pressurized to 6 atmospheres with compressed air, and a patient breathes in a mixture of gas that is 47% oxygen by volume. In another protocol, a separate protocol, let's call it the second protocol, the chamber is pressurized with a compressed air to 2.8 atmospheres, and the patient breathes pure oxygen gas. Determine the partial pressure of oxygen in each treatment protocol and compare the results. We would maybe expect them to be similar if they are the same sort of treatment option, for example. All right, so for that first situation, we are given the molar ratio of oxygen, right? It's 47% oxygen. So we can just plug that in times the pressure total. We're at 6 atmospheres, and that will get us the partial pressure of oxygen gas. Okay, so we have 0.47 times 6 atmospheres. That's 2.8 atmospheres of partial pressure for oxygen. Secondly, for the second situation, it's pure oxygen. It's 100% oxygen. So our molar ratio for oxygen is 1. So our partial pressure of oxygen is our pressure total, which is 2.8 atmospheres. So the point of this is that both protocols actually give you the same partial pressure of oxygen, which is much higher than what you would get from from breathing in atmospheric oxygen. Atmospheric oxygen is about 21% of the moles of air that you're breathing. So it's only about 21% of the pressure total. So at normal atmospheric conditions, you're only breathing in 0.21 atmospheres partial pressure of oxygen. So you can see that this is a very marked increase in the partial pressure of oxygen. And that's exactly the point of these hyperbaric chambers, is you're trying to force in as much oxygen as possible. Well, not as possible, but a large increase in the amount of oxygen that you are trying to give these people to help them deal with certain conditions, like too much nitrogen in the blood, which is called the bends. If you've heard of that in diving accidents, if you surface too quickly, for example. So so this is an interesting kind of, again, an application of understanding what they're really going for in terms of partial pressures.